very much. Yes, hello everybody, my name is Jonas. I am originally from Switzerland, but for the past 5 or so years I've been living in Tokyo, and I work for a company in Tokyo called HDE, and we are hiring very much. If you're looking for a job, please come talk to me afterwards. As you can maybe see on the screen, this is all going to be happening in a IDE. Oh, is it not on? That's not going to work. Test. Can you hear me?
Yes.
Better? Oh, okay, great. Yeah, sorry. So yeah, this is all going to happen in an IDE, and the text will be small. If you're sitting at the back, right now would be a good time to move to the front if you can't see. And yeah, the talk title is Artisanal Async Adventures. So we're going to talk about asynchronous networking. And the artisanal part is because it's going to happen all in front of your very eyes over the next 30 minutes. And the goal of the talk is that at the end of the talk you will have a better understanding of what is asynchronous networking, how does asynchronous networking work, and why does it work, and why you might want to use it. So let's get started. And to get started, we need a problem that needs solving. And the problem that I have is I came up with an algorithm. It takes a number and it returns a number. And I'm going to implement this complicated algorithm right now for you. So we'll take the number and add 42. Now, this amazing algorithm I want to share with the world. So I want to build some sort of server that my customers can talk to and consume this service. Now, of course, I could use Flask, I could use Django or anything or stuff like that. But HTTP is so super high level and bad performance that we really need something more low level. So we're going to use the socket library. By the way, this is all going to happen in Python 3.6. I haven't, and we're going to use type hints. So yeah, we're going to use socket module. So we're going to implement a server. The server will listen to an address, and because it's a server, it will run forever and not return anything. Now, an address for a server is a tuple of a string, which is the host, the interface we want to bind to, and an integer, which is the port we want to listen on. So, how to do a socket server in Python 101? Well, first of all, you're going to import socket. By the way, this is PyCharm, and I'm going to use some magical functions of PyCharm. Please don't be afraid. I'm trying to explain them, so I told PyCharm to import it for me. So we're going to create a socket of address family internet and of type sock stream, and what this means it's a TCP/IP socket. And we're going to set a We're going to set the reuse address option because that's what everybody does. I'm not 100% sure what this does, but it seems to be good. Then we tell the socket to bind to our address, and we will tell it to listen on that address with a certain backlog. Sock.listen turns a socket into a server-side socket, which is exactly what we want. Now, a very common pattern in a server is that you have an infinite loop, so we will also have an infinite loop. And in this loop, we will accept connections from clients and then handle these connections. So the way you accept connections from a client is you call the accept function on the socket object. The accept function returns a tuple of a client socket and client address. So we're going to do some very simple logging. I'm going to say connection from this address, just so we know. And then we want to keep our server function nice and clean and neat. So instead of handling the connection or the client right here in this function, we will call another function with the client. So we have to implement this function. And our handler function takes a socket. And it also returns nothing. And because I'm going to expect billions of people to use my service, we don't want to just handle one request per connection. We want to allow the client to reuse the connection. So we're going to again do an infinite loop. And we are going to read some data. We're going to read the requests from the client. The way you do that is you call receive on the socket object and give it a number of bytes, which is the maximum number of bytes you want to read. And yeah, it returns a byte. If nothing is in the request, we're going to assume that the client is done with all their work. So we're going to close the connection and return. If there is data, we're going to assume that it's ASCII encoded integer. And even though the request is bytes, if we give those bytes to int, Python will assume it's ASCII encoded numbers, and it will actually turn it into the correct integer. That's a lovely little thing. Then we're going to call our algorithm with the number and get the result, and now we need to give it back to the client. So we send it to the client, and we add a new line so that our customers can easily consume this API. This needs to be bytes, so we'll encode it as ASCII. And now, assuming I've made no typos or mistakes, if I call the server function with a tuple of an address that we can bind to, and then run this, so the file is called apply. Now in a different tab, I'm going to connect to that client, and the way we're going to do that is a tool called netcat, shortened to NC. And netcat is the easiest way, basically, you can talk to a server from a Unix-based system. It's a bit like cat or echo in your shell, but it talks to a server instead of local stuff. So we can connect to our server with NC localhost 3033, and then I'm going to need a number from somebody, a number between 0 and 100. 42. 84, beautiful. Now, as I mentioned, billions and billions of people are going to use this every day, every second of their lives. So we're going to simulate another one of those billions of people. I'm going to connect, and can somebody else give me a different number?
10.
10. Ah, wait, I accidentally closed. Yeah, so I'm going to do this again because I screwed up. Okay. So yeah, the first customer wanted 42. Second one wants 10. They want 10. Yeah, so this is a bit problematic. Like the first one can get 10. It still works. It's fine, no problem. So what's happening? Problem is that our server is blocking. It can only handle a single connection at any given time. Why? Because Python, by default, will run single-threaded everything one after the other, nothing special. So in the server, it will hit the while loop, and it will block on line 29 here until a connection comes. And when a connection comes, it will call the handler function with the client. And in the handler function, it will, first of all, block here until we receive data from the client. Then it will block down here until we can send data to the client. And then it will go back to the top of the loop and do this until the client is done. So we need to do something to handle more than one connection at any given time. We could use threads, we could use multiple processes, but threading in Python is a bit tricky. It has quite a big overhead. Multiple processes has even more overhead because you need to run multiple instances of Python. So instead, we're gonna use a new feature in Python 3, and that's async await. And Python 3 added a new keyword to Python, and that is async. So instead of defining normal functions, you can call your functions async functions, and now you have asynchronous functions, and this will work perfectly. So we're going to, again, go to our app terminal, and I will run the app, and it immediately exits. This is awkward. We have a server. It has a while true loop. It should run forever, right? But somehow calling this function doesn't actually seem to do much. So we're going to do a little bit Python functions 101. I'm going to open up an IPython shell, and I'm going to declare a function foo, which prints bar. If I call this function, it prints bar. So far, so good. Now, if I do an async function foo that prints bar, and I then call this function, it doesn't print bar, but it returns a coroutine object foo at some memory address. So what is a coroutine object? So instead of just, let's catch the return variable, and if we inspect this, and that's a neat feature of IPython. In IPython, if you type a variable and then a dot and then hit tab, it will give you the available methods and properties on that object. So we have a close method, we have a CR await, CR code, CR running, etc. But because I've read the documentation for you, I know that the send function is what we're interested in here. The send function of a coroutine object takes one argument, and in the simplest case, if you just give it none as an argument, and this happens. So this looks very scary and bad because it raised an exception, but interestingly, just before the exception, it printed bar. And then it raised stop iteration. So coroutines are very similar to generators in that they can suspend their execution until something that manages that coroutine tells it it should move on to the next point. And in the case of coroutines, it's you call the send function, and the send function will advance the coroutine up to its next point where it has to stop. And if it's done with everything that it wanted to do, it will raise a stop iteration exception. So this exception is actually part of the protocol and exactly what we expect. And now before I continue, I need to explain one more thing. And this is going to look a bit scary, but we're going to define a class foo, which has a method, double_await. This is not an async method. And we're going to yield something in that method. And now we're going to redefine our foo function, and we'll await an instance of our class in here. async.foo. Now if we again call foo, nothing special happens. But now if we coroutine send none, we get 42 as a return value of the send method. And this 42 comes from this await yield, method of the class foo, where it yields 42. Yes?
If you would now call send again in command.
I'm gonna call send again. If we call send again, it just raises a stop iteration. Why? Because in our async.foo, we await foo, so it can run until that point in the first send, and the second send, there's nothing after that statement, so it's just done. So that's all fine and interesting, but how does it actually help us? So clearly, just async is not enough. We also need to await things. And what can you await in asynchronous networking? I/O. And in our code, we have 3 points where we do I/O. We have the accept call, because that blocks I/O until there's a connection coming. We have the receive call on the socket, which blocks until there's data. And we have the send call on a socket, which blocks until it can send data. So we need to change those to await. The problem is the socket module in Python doesn't support async await, so we have to implement our own API. So we'll say we have an async receive, which takes a socket and a bunch of numbers, a number of bytes. We're going to say we have an async send, which takes a socket and a bytes object. And we say we have a async accept, which takes a socket. So let's implement these. So async accept takes a socket, and it returns a tuple of a socket and an address. And as we saw before, if we have a coroutine, we have a way to advance it. And if we have a double_await, we have a way to signal from inside a coroutine to whatever is running the coroutine that we have some information. So we will say that we want to await an object. And we're going to do it a little bit like a domain-specific language. And so we will have a can method. And this takes an action and a target. So yeah, if I used 3.7, I could use a data class here, so maybe I should update. And the action we will just define as an enum. Import enum. And this has a receive and a send action. So we will say wait until we can receive on this socket. And when we can just call receive on that socket. Accept, sorry. Oh yeah, we need. So in the await of this class, we just return the action and the target. And then for async receive, which takes a socket and a number of bytes, it wants to read and it returns bytes. We again say wait until we can read on this socket, and when we can, we will just read on this socket. And you can probably see where this is going for async send, because it takes a socket and some bytes. We say await until we can send to this socket, and when we can, we do. And that's all fine and good, but we still have no thing that can actually run any of this code. And so we are going to define a new type, and I'm going to call this type a task. And a task, as I define it in this code, is some Python code that we can and want to run. So coroutine objects are tasks. So in the server, instead of calling the handler, which does nothing because handler is async, we say add task. So add this task to a list of tasks that we want to do. And in the end, when we run the server, we also don't just run it, we say this is a task that we want to run. So add this task, and then we will say run these tasks. So what does the add task function do? It takes a task and it returns nothing, and we're just going to add it to a global list of tasks. I say list, but I'm using a deck here. If you're not familiar with a deck, it's a double-ended queue. It's very similar to a list in Python, but it's efficient to add at either end and take from either end. And that's the only thing we want to do here, so that's perfect for our task. So in add task, we simply add the task to a list of tasks that we want to run. This is not that interesting. The interesting part will be the run tasks function. So run tasks takes no argument, returns nothing, and it will, while there are tasks, it will run. And while there are tasks, we will get a task. So we'll just get the first task. We will then call send on the task object. So again, task objects are coroutines, so we can. If there is a stop iteration, this task is done and we can forget about it. Now, because of this await can action target thing that we did before, the send function will return a tuple of an action and a target. So depending on the action, we will do different things. If the action is receive, do something. If it's send, do something else, and otherwise raise an exception because something went wrong. So what do we do when we know that a coroutine array wants to read on a socket? Well, very simply, we will add it into a waiting room, in a waiting area where it can wait until it can read. So we will define two more objects, and those are dictionaries of socket objects to tasks. And one is for sockets that are waiting for sending, and one is for waiting for receiving. So if the task wants to receive, we simply put it into this waiting area, into this dictionary, and if it wants to send, we will do the same, but put it into the send area. So we now have a run loop that can advance coroutine tasks to their next step, figure out their action, and move them into an appropriate area. Now what we also need is a way to move those tasks back out of the waiting areas into the task queue when they can do something. So first of all, because the tasks move out of the task queue, we need to change this while loop to while there is any tasks that are active or while there's any in either of the sending areas keep running. Now in the next line we try to pop from the tasks, but if there is no tasks we need to do something. So while there are no tasks, we need to move tasks out of those waiting areas back into the task queue. How do you do that? Well, luckily in Python, there's in the standard library a module called select. Select exposes a function called select. Select takes 3 arguments. The first argument is a list of sockets that want to read. Well, we have this waiting area where there is sockets that want to read as the keys, so we can pass this dictionary in. The second argument is, again, a list of sockets that want to send. We have a waiting area of sockets that want to send. Perfect. The third argument is not important for here, and I will skip over it. And the return value of this is a triple of a list of sockets that we passed in that can read right now, a list of sockets that can send right now, and again, a third value that is not important. So we pass it in everything that wants to read, everything that wants to send, and we will pull out those that can read and those that can send. What do we do with those? So for each socket that can receive right now, we move it out of the waiting area back into the task queue. And we do the same thing for those that can send. And now, believe it or not, again, assuming I've made no mistake, this should actually work. It's a big assumption. So if we again connect from one tab, say 42, and then we connect from another tab, and we say 10, they now work. Hey, we can even have a third tab and do 3. So in about 100 lines of Python, we have turned our blocking socket server into a non-blocking socket server. And you might say that, like, wow, this is all nice and fancy, who cares really? Like, I would not ever use this. I would use something real, like Tornado, like Twisted, like Async.io, or Node.js maybe. Well, the fact of the matter is that all of those things I just named basically work the same as this. This is actually how those things work. Yes, they do error handling and all these fancy things, but at the core, they will have something similar to this run loop where they run code. And this is more or less my talk. I know this was very fast and very complicated, but I have one more bad news for you, and that is this talk actually comes with homework. Because what I want you to do is, when you go home tonight or tomorrow, to sit down and do what I just did yourself. Try to actually implement an asynchronous networking solution by yourself. You're allowed to use my talk, the video of my talk, as a guide. You don't have to do it in 30 minutes, and you don't have to do it in front of people. You can do it at home, and you can read the documentation and everything. If you want to do a little bit of extra work, instead of using select.select, if you are on OS X, Mac OS, use select.kq. That's again in the standard library, it's documented, and try to figure out why that would be better. If you're on Linux, use select.epol, and again, try to figure out why this is better than select.select. And if you're on Windows, use select.defpol, which again is better than select.select. And yeah, I think my time is also up, so with that, thank you very much for your attention.
Thank you very much. So I'd like to open the floor now for questions. If I can start. So what is the limit on the number of connections that a solution like this can handle? And does it differ from any of the existing solutions like Tornado that you mentioned?
So again, Tornado is the same as this solution, more or less. what Async IO, Tornado, and Twisted do is they abstract away that select.select and they use the most efficient tool on each platform to implement this loop. Now, select.select is the worst of all of these tools, but it's the simplest, which is why I chose it here. So select.select scales to maybe a couple of hundreds of sockets. There's a strict limit, but I don't actually know. I don't remember the number off the top of my head. If you use something like ePOL or KQ, you can do tens of thousands or more. It's at some point you will be limited by your hardware, because one of the strengths of this versus a threaded approach or multiprocessing approach is that it is very, very low overhead. We only have one Python process that we need to run here, not multiple processes which all need their own interpreter and everything. You don't have to do thread synchronization or anything like that. It's just a single thread. And each of our tasks that we want to run are always either in the task queue or in one of those two dictionaries. So they just move around there, and there's never duplication or anything. So it's extremely efficient in terms of memory and CPU overhead. But yeah, one of the big points of asynchronous networking is to be able to scale a single server to tens of thousands of connections.
Thank you very much.
I think there's a...
Okay.
And what if we want to connect multi-threading into the asynchronous framework?
Okay.
We have workload.
Sure, yeah, that's a very excellent question, because if you want extra homework, make threads work with this. And the way you make threads work with this is you use threads like normal, but you need some way to integrate it into the event loop, right? And the way you do that is you create local socket connections, and you handle one of them to the thread and keep one in the main thread, and use like read and write to signal when it's done, when the thread is done, basically. So you can do in Python, you can do, what is it, socket something, socket pair will return a tuple of sockets where you hand one of them to the thread, keep one in the main thread, and then you basically await on those sockets to see if the thread is done or not. It's a little bit tricky to do, but yeah, that's basically how you do it. You abuse sockets to make threads work.
So basically, you have the workload in another process.
That's the other alternative, of course, is that instead of using multiple threads, you use multiple processes, and you use a sub-process, and then again you use the file descriptors of the sub-process and use those in the await statements to see if your workload is done. Yeah.
Any further questions?
To add to that comment that to maybe reduce the amount of homework to do the
yeah,
to do the between thread communication, you could use something like 0MQ, for instance, which I think is very excellent.
of course. Yeah.
And low overhead and easy to get started, but you still actually have to do some of these.
Yeah, so you could use
Like
something like
this
0MQ, of course, but at the end with 0MQ you still have a socket. So you're doing something very similar to just do it yourself. But yes.
But my point is like, Tornado is like really high level abstract, and then there's your like do it yourself approach, and then 0MQ is kind of, at least in my experience, like in between. So it's a nice learning, like before you go to that, you can play around with 0MQ, and then I think it's a good learning curve.
Maybe. I'm not an expert on 0MQ, so I can't answer that.
It's just a suggestion.
Yeah.
Thank you. Any further questions? Okay, so then let's thank the speaker once more.